Hello class, here we are, lecture 8. We're gonna continue on the theme we started last lecture in exploring other linear models, other Gaussian field theories, moving away and generalizing from our focus over the last few weeks of the Gaussian fluctuations of the density field. Last lecture, we talked about how one could apply the same sorts of techniques to understand effective interactions that proteins might experience in a membrane. And today we'll think about how you apply these same sorts of techniques, but in a quantum mechanical context. And specifically, we'll consider the problem of an excess electron in a lattice, a model appropriate for, say, band carriers in a semiconductor. So the picture that you should have in mind for this discussion is imagining we have some lattice, a regular arrangement of heavy nuclei, like maybe here shown as some simple square lattice. And in that lattice, we're going to place a charge. Now that charge is an electron, could be photogenerated, and of course is intrinsically quantum mechanical. Now from a purely classical perspective, if you put an electron in a polar media, like we're imagining this lattice to be, imagining that it can it has partial charges on different types of atoms in the unit cell. A negatively charged electron, or negative excess charge, like an electron, will then be expected to couple to that surrounding lattice. If, for example, the atoms that I've drawn all have positive charge, we'd expect there to be a surrounding polarization that moves those lattice particles close to the electron. You can imagine, even though I'm drawing these as spheres, maybe they are little dipoles that are then polarizing in response to the electron. Now, there's already something a bit misleading in how I started this picture, in that I put the electron somewhere definite. It had a center. I've represented that charge distribution with this little red blob. I've imagined it's already localized, and that's not exactly right. If we were at zero temperature, if there were no disorder, Bloch would have told us that the electronic states are delocalized. They're plane wave states, owing to the periodicity of the lattice. The localization of an electron, however, could be generated by the dynamic disorder that is accompanying this polarization field. So when an initially delocalized electron couples to the surrounding lattice, it would, in polarizing, it would generate a potential minima that might trap that electron. Coming from a more chemistry background, this is really analogous to imagining putting an ion into a polar solution and seeing the dipoles of the solvent reorient in response to that ion. The electrostatics then would generate a favorable solvation-like energy for the electron in connection to lattice. Now, in the ideal case where this lattice continues on infinitely far in extent, it has a translational invariance. If I move a unit cell, I recover the same structural environment. So there's a symmetry breaking which is dynamical that has to do with where the electron is. But the electron, from the perspective of the lattice, all sites are equivalent, so the electron must see all sites being equivalent. So statistically, we would expect the electron to still move through the lattice. But at each point, we expect this physics of polarization, of trapping the electron, to still occur. So really the right picture for an excess electron in this polar lattice is that as the electron moves, it carries around this polarization field. So if we add the electron with a polarization cloud that it generates, what we get is an object first named by Picard, known as a polaron. That's the dressing of an electron by the displacement, the surrounding displacement field of a polar lattice. Now, as you can imagine, if as the lattice moves, or as the electron moves through the lattice, it has to carry around this polarization. It has to move the lattice with it. It's not going to move as fast as it would if the lattice wasn't being deflected and perturbed in its vicinity. So to the extent that that electron carries around this displacement field, you might expect that it moves more slowly. If to the extent the electron moves ballistically, one can summarize how fast it moves through a lattice just by knowing its mass. You have some characteristic momentum associated with the band that it's moving through. That's a good quantum number, absent these phonons. And so if I know the momentum, I could determine the velocity just with an effective mass. So often this object, the polaron, is characterized by an effective mass, which is some semblance of how much extra mass is accommodating the electron as it moves through the lattice due to this displacement field. If we call that effective mass m star, we expect it to be greater than the original band mass of that electron. In addition, you might actually ask, what is this solvation energy associated with the electron interacting with the lattice? That's a favorable interaction. That is typically called a binding energy. We'll denote delta E. In the limit that the binding energy is very large, and the effective mass is also, the binding energy is large and negative, the effective mass is large and positive, there can be a localization which happens spontaneously. Again, all sites are statistically equivalent. However, if the electron becomes significantly localized, it might take a very long time for it to move through the lattice. For all intents and purposes, you could imagine that it's trapped. You would call this a self-trapping phenomena. It's not like the electron finds a defect and gets stuck there. Rather, it generates its own stable state due to this feedback by polarizing the lattice, created by polarizing the lattice. So this concept of a polaron, it dates back really to Landau, who really was the first one to think about the notion of a dynamical trapping of an electron's ability to get stuck somewhere in the lattice because it interacted so strongly with the polarization field due to the heavy nuclei. And subsequent to those initial studies, there was an effort to write down kind of a simple Hamiltonian that would describe this behavior. And the canonical model that emerged is due to Froelich. Good German guy with an umlaut in his name. He said that, well, maybe you could describe this electron as a sum of three terms. I have some kinetic energy for the electron. Maybe at low enough temperatures, I can imagine that the lattice are really made out of harmonic oscillators. There are, of course, a number of different oscillators. Due to the periodicity of those oscillators and the couplings that you might imagine they have between each adjacent particle in the unit cell, it's not really that the individual atoms in the unit cell vibrate independently or as with simple harmonic motion, but rather there exists some set of normal modes which are uncoupled. In a lattice, you would call those phonons. So he imagined that he could write down a set of phonons indexed by K, which were then all independent, had their own kinetic energy, and additionally exhibited a harmonic restoring force around some zero net displacement around their characteristic unit cell, unit lattice position. Typically, phonons are expressed in mass-weighted coordinates, so there's no mass associated with the mass is essentially in the definition of the lengths, but they do have some characteristic frequency. We'll denote here omega of K. If that was all that we had, we would have a separable Hamiltonian for the electrons and for the nuclei. So there was, they would not exhibit any force or interact in any way. So we have to include some sort of interaction term. And the model that Froelich wrote down, imagine that he could characterize that interaction just with electrostatics. So imagining really that the lattice was a continuous medium that was polarizable and used something known as dielectric continuum theory to work out the expected interaction energy for a charge and the dipole or polarization field that a lattice could generate in response to that charge. So one could write this down. The dipole generated in response to a field is got a magnitude that goes like the extent of the displacement of each of those oscillators. It depends on the position or where the particle is, but in K space, we can write down that position as a Fourier wave. And the coupling of a charged dipole is something that goes like 1 over K. You can rationalize that that is the K dependence by remembering that if a charge interacted with another charge, it would go like 1 over K squared. That's the Fourier transform of the Coulomb operator. A charged dipole is the first term in a multiple expansion. Multiple expansion is a gradient expansion in that Coulomb operator. So I get one gradient of the Coulomb potential in Fourier space that would bring down a factor of ik, canceling out the one of the k's in the 1 over K squared. So the x here, little x and little p, those are the operators for the phonons. The capital P and capital X, those are the operators for the electron. And in addition to this dipole charge coupling, there is some strength, some kernel associated with how much dipole you expect to get, which we'll discuss in a second. And Frolick introduced a dimensionless parameter, alpha, which is a coupling constant. So let's go through that. So first, I'm writing down these sums as sums over wave vectors, just to be very clear about the notation. That sum over wave vectors is just a compact way of saying the Fourier transform. So I don't have to bring around factors of 2 and pi, and also don't imagine that this is a discrete Fourier transform, so there's no factors of 1 over the square root of the volume. This kernel, V of K, the strength of that charged dipole interaction, if you work out the continuum electrostatics, will go like the frequency of each of those oscillators, essentially times how much displacement I expect to get due to the charge. So there's factors of the frequency and the band mass of that electron. And finally, this alpha, the dimensionless coupling constant, it is given by some material properties which are imagined to be easily measurable. So it has charge on the electron reflecting the initial Coulomb coupling. It's got a square root of that band mass. The frequency of those oscillators. And then depends on the so-called Picard factor, 1 over the infinite frequency dielectric constant, less the static, 1 over the static dielectric constant. Okay, so those are all the definitions. In addition, in this limit where you could treat the problem as a continuous problem, where you're working just with the continuum electrostatics to derive this interaction, which if you're really interested in, Feynman in his statistical mechanics book does a good job of. One realizes that the characteristic dispersion of a polar lattice, the modes that couple to a charge are just polar modes. The lowest energy mode which could couple is known as the longitudinal optical frequency. The dispersion of that frequency goes like k squared. So for small k, it's essentially a constant. So actually, in the original treatment of the polaron problem, and is now standard, one imagines that these phonons are actually dispersionless and just given by a constant frequency, the so-called longitudinal optical mode. Okay, so then provided some dielectric constants measurable through a dielectric spectroscopy or a capacitance measurement, a longitudinal optical mode, factors of fundamental constants like Planck's constant h bar, charge on the electron, we have essentially everything we need to know to parameterize this Hamiltonian. It's worth noting that these dimensionless coupling constants for something like a fairly non-polar or very rigid semiconductor are pretty small. So like 0.7 for something like gallium arsenide. And for very polarizable lattices, like strontium titanate might be around 3.77. The famed halide perovskites, which are all the rage right now, have a coupling constant that's intermediate to those two kind of extremes, somewhere around 1.8 to 2. Okay, so then this is the Hamiltonian. Let's clean that up. Those blues look very ugly. It's quantum mechanical in that these dynamical variables, the x's and p's, are operators. But it is bilinear. So we get, at least in the phonons, we have x, little x quantity squared, little p's quantity squared. The kinetic energy for the electron is also a quadratic variable. Only this interaction looks kind of complicated. However, it's only complicated due to the electronic degrees of freedom. It's linear in the phonon variables. So from the perspective of the phonons, we have a Gaussian Hamiltonian with a linear coupling to the electrons. So if this was not quantum mechanical, we would know how to proceed. That's a Gaussian field theory in a kind of expected sense. We expect harmonic oscillators to be Gaussian random variables. This just has a lot of window dressing associated with its coupling to the electron. Now, it's not classical. Those are operators entering into the Hamiltonian, which I will try to continue to denote with hats. And so it's not at all obvious how we apply a Gaussian field theory to a quantum mechanical system where those operators are important. So before we actually tackle this system, trying to tease out some of the physics of the Frolic model to understand, for example, what that binding energy is, and what are the effective interactions on the electron that are generated through the fluctuations of this Gaussian field from the phonons, we have to figure out a way to put this problem in terms of our Gaussian field theory. We need to figure out how to turn this quantum mechanical problem into a classical problem. That sounds like a tall order. And indeed, if one is interested in the dynamics of a system, it's impossible. And that's because, of course, quantum mechanically, there can be coherences, there can be tunneling, very non-classical motions that won't be described by some effective classical model. However, if one is interested in the thermodynamics of the problem, the energetics, it turns out that there's a way to represent a classical object in an extended phase space with extra degrees of freedom that turn it into a classical problem. This is known as a quantum classical isomorphism. It is a mapping of a quantum mechanical problem into a classical problem, where the classical problem has more degrees of freedom. This was first derived and employed by Feynman. We will see that it employs the path integral description of quantum mechanics and was really popularized in chemistry to treat complicated molecular problems by Walnes and Chandler, and is now a very practical tool for simulating quantum mechanical systems by studying slightly larger classical problems. Okay, so to understand how this quantum classical isomorphism is, I will derive the path integral description of the quantum partition function, and we'll see that it boils down to just a classical calculation. So let's assume we have some Hamiltonian which satisfies the time-independent Schrodinger equation with set of eigenvalues E and eigenvectors epsilon. The partition function associated with that system can be written down. Let's use Z as the partition function. We'll even really emphasize it's the quantum mechanical partition function, give it a subscript QM. If I know those eigenenergies, E sub I, the partition function takes the same form as it always would. It's a weighted sum over those energy levels, where the weighting is just a Boltzmann factor. That's our definition of the partition function. It is true quantum mechanically or classically. Just how we go about computing those energy levels is very different. Now, to get those energy levels, I would need to diagonalize the Hamiltonian. that's a fundamentally quantum mechanical operation that I would have to undergo. I could revise the statement of the partition function by rewriting that weighted sum of Boltzmann factors as a weighted sum of a Boltzmann operator, that Hamiltonian, acting on its eigenfunction, like so. Since we've assumed that H is diagonalizable with a set of eigenfunctions epsilon I, e to the beta, the Hamiltonian acting on that eigenfunction, gives me back the Boltzmann operator with that energy, with the corresponding eigenenergy. That is no longer an operator. And noting the orthogonality that must exist and the normalization that must exist for that set of eigenfunctions being 1, I've just introduced 1 in a really complicated way. But this is a really useful way to rewrite the partition function, because now it is a sum over a set of states. The expectation value of this specific operator, the Boltzmann operator, that is mathematically known as a trace operation. And what's convenient is a trace is independent of the basis. I could choose to sum those states up in any manner I want. It's convenient, of course, if I know the eigenfunctions to do it in that basis, but the expression of the partition function as a trace tells me that I could, if I wanted to, project those functions into any more convenient basis to carry out that sum, and I'll get the same answer. So for systems like our frolic Hamiltonian, or most chemical systems, the Hamiltonian typically has a kinetic energy part that depends on a momentum operator, and a potential energy part that depends on the position operator. Because this formulation of the partition function as a trace, I could, if I wanted to, compute that partition function by summing over the real space eigenfunctions denoted with the Braun-Ketz x, like so. That would be choosing a specific basis of real space functions. Those functions would need to satisfy a completeness and an orthogonality. Mathematically represented by a resolution of the identity and orthogonality through the Dirac delta function. Now, the kinetic, if we only had a potential energy operator, that would be a really simple calculation to do. The potential energy acting on a set of real space functions, the potential energy is diagonal in that set, so it's easy to compute those matrix elements. However, the kinetic energy operator, of course, is not diagonal in the set of real space functions. Its action on those real space functions is therefore complicated. It will behoove us to introduce a set of plane wave functions that diagonalize that kinetic energy operator. Those states would also need to satisfy a completeness. And orthogonality. Just means that I can create a full Hilbert space from those states. And because we're introducing both real space and plane wave and K-space states, it will be useful to note the representation of a plane wave state in real space as a plane wave. Indeed, that's why we call it a plane wave state. Okay, so there's some linear algebra on the set of functions, defining Hilbert spaces in real space and momentum space. Indeed, the rationalization for introducing all those is to note that our Hamiltonian has a momentum operator which is diagonal in the state in the p states, and a potential energy which is diagonal in the real space states. Now, if what I want to do is to compute this partition function, I have a bit of a problem, indeed, because to do that would be to know the whole action of the Hamiltonian on the set of real space states, which I don't. That would essentially be to diagonalize that in that state, which would require me to diagonalize it, find its eigenvalues, and then project those, eigenvectors, then project those in real space. Rather than doing that, I will employ what's known as a Trotterization or a Trotter expansion of that exponential operator. The fact that the Boltzmann operator has a kinetic energy part and a potential energy part, x and p do not commute as a function, and as a consequence, I cannot factorize that exponential. That would assume that those two operators commute, which they do not. And a Trotter expansion, however, will let me rewrite it as a factorization, which is mathematically exact. I can write this Boltzmann operator in the limit of an infinite series. There are many degenerate ways to write this down. I will choose to write it down like this. I can pull out the potential energy, separate it from the kinetic energy, and symmetrize it. This Trotter expansion is exact in the limit that the number of slices is infinite. That looks like I've made my life a lot harder, but let's define this little thing as I sub n, and let's try to manipulate I sub n. Specifically, let's introduce a couple resolutions of the identity, the completeness relationship for real space states. It's an integral over some xi, an integral over some xi plus 1. Let's also introduce a set of k-space states, or momentum states. Let's put the xi here. Let's put a set of k-space states between it and the kinetic energy operator. And another set of real space states. There. Actually, let's put that here. Okay, so that's an exact operation in one of those n factors in the Trotterization, the Trotter expansion of the Boltzmann operator. But now note this. If I act U, the potential energy operator, on a set of real space states, it's diagonal in that set. I will turn it into that function evaluated at the number x, not the operator x. Evaluated at that point, xi. Analogously, I could act the kinetic energy operator on a set of states it is diagonal in, giving me the kinetic energy at that momentum, pi, and those states back. And the same thing with that additional potential yielding integrals over states, xi plus 1, and pi. And now I've gotten rid of all of the operators at the expense of having now to compute a couple overlaps. So I have xi, the overlap of xi with pi, and the overlap of pi with xi plus 1. But I've already introduced what those states look like. That the projection of the momentum state pi into real space is e to the I pi xi analogously, the projection of the complex conjugate of the projection of pi into xi plus 1 is e to the minus I pi xi plus 1 over h bar. So now I actually have a full representation of this little Trotter slice in terms of an evaluation of a potential at a couple real space points, xi and xi plus 1. And a momentum integral, if I unwrap what the momentum must be for a single particle, that's just momentum operator squared divided by twice the mass of whatever particle I'm considering. I have a factor of n from that Trotter splitting. And now I have something that is linear in that momentum. Depends on the difference of these two real space positions up to some normalization constant. Now, if you look at that, momentum goes up in the argument of the exponential squared. That's a Gaussian distribution. And I have something linear in P, so that's an integral we know how to do. Doing that integral, we find factors of 2 pi n in the mass, pi's, and h bars. I'm missing a factor of beta. From the variance of that momentum integral. I'm left over with these integrals over space still. The potentials evaluated at those positions. And now an additional term that depends on the positions that looks like this. The difference in the positions I plus 1 squared, that looks like it's harmonic in the positions. It looks like it's a potential with a spring constant that depends on the number of these Trotter splittings, h bar and beta. Now for each one of those factors of in that initial splitting, I could do this over and over again. If I collect all of those, what I'll have is a representation of the partition function in a large number of these component limit constants. And now in integrals over real space positions, weighted by the collection of all of these arguments, which I will define as a function s that depends on that set of positions. That function s, called an action, is equal to beta times now a sum over I from 0 to n minus 1. Minus 1 because this projector at the end of each component gets put under this initial trace operation, meaning that those boundary terms have to be cyclic. And the action has the form beta times a sum 1 by n squared m xi xi plus 1 quantity squared divided by twice beta h bar beta squared h bar squared plus the original potential evaluated at each one of those points. Now look at that. We started with 1 degree of freedom, some x position, and its conjugate momentum quantum mechanically. None of those variables, the x's, are dynamic. So those are classical variables. They're just numbers that can take any of a continuous value. We have an exponential of this action, which goes like minus beta times some quantities. That looks just like a potential. The whole thing looks like a Boltzmann distribution over an extra set of variables with a new effective energy, which is the original potential evaluated at each one of those points less or divided by the number of these Trotter factors. And in addition, there's a harmonic potential between each one of these slices, a restoring force in this abstract slicing of space that acts like a little spring with a constant that depends on temperature, the mass of the particle, and h bar. If we define a tau as a unit of time is beta h bar, indeed that has units of time. The uncertainty principle delta E times delta T is equal to h bar tells you that if I take h bar over an energy, I get a time. In the limit that n is large, I can think of an infinitesimal change in some time as a limit where that n is really large. That's the limit we want to work in. So I can take a continuum limit, take this limit as n goes to infinity, and what I will get is that action becomes continuous. So n squared over beta h bar squared, that's what I've just defined as a delta t quantity squared. And the limit that n is infinitely large, the difference between xi and xi plus 1 over that gets really small. That's essentially a difference expression, a finite difference expression for the derivative of x with respect to t. That whole thing then gets quantity squared. So I'll have an infinite number in the sum. I can turn that into an integral with a measure delta t. Up to that factor of m, that is then xi, or x of t, the derivative, quantity squared. I have a factor of 2 and m remaining. And in addition, I have my potential evaluated at each one of those points. Left over a factor of h bar, and this time goes between 0 and beta h. So what I have now is the continuum limit of that discrete action. And what it looks like is a kinetic energy operator in this odd sort of time set by beta h bar. In addition, I have my original potential operator. And so what I've gone, the interpretation of this is that I start with a quantum particle, I end up with a classical particle with a set of springs that tie together points in this fictitious time. And the subsequent partition function is now an integral over all of those paths in that imaginary time, weighted by that action. The trace operation imposes that x evaluated at 0 time is x evaluated at beta h bar in time. So it's a sum of periodic paths in an imaginary time that take apart a quantum particle, or no, a classical particle between a time 0 and a time beta h bar. This is known as an imaginary time path integral. And to compute it just requires us to study classical mechanics. The kinetic energy classical is a time derivative of some position, the potential energy along that path. But now for each place the particle can be, there are little loops little trajectories that act to delocalize essentially that particle, introducing all of these extra degrees of freedom. So that is the quantum classical isomorphism. It has turned our quantum calculation with operators into a classical operation, a classical partition function, now in an imaginary time. So now let's go back to our polaron problem. Translating that original Hamiltonian into an action, we'll have a piece from an electron. And we know how to write down the kinetic energy operator turns into a kinetic energy factor. We'll have a piece due to the phonons. Each of them are independent and distinguishable. And then a coupling. Call it EPH or EP, which weights that optical phonon frequency, the square root of our dimensionless coupling, factors of constants, this kernel, and then our imaginary time path over each mode, the displacement of the kth oscillator, and this Fourier transform of the electron position. So the partition function is an integral over all the paths the electron can take. all of the paths all of the phonons can take, weighted by the electron action, the phonon action, and the coupling. Now note the phonon, so now this really does look just like our usual field theory. We have an integral over a continuous field. Now the field is a little bit different in that it's a variable in how it traces out paths in this tau, this imaginary time. The electron is nonlinear. It has a quadratic bit due to the kinetic energy, but this complicated bit in the kernel of the electron-phonon coupling due to the complex exponential. But the phonons are Gaussian. And has linear coupling to the electrons in that coupling. So we could use our tricks to evaluate partition functions of Gaussian path integrals or Gaussian field theories to integrate out the phonon variables and see what remains for the electron. So let's first note that we can indeed rewrite that phonon action if we were to do so by diagonalizing it, figuring out what its correlation function is. Do that by uncoupling. So right now, different points in imaginary time are coupled through this differential operator entering in from the kinetic energy. We could write that by introducing a Fourier transform in frequency or in time. And we would get now independent modes evaluated at all the different frequencies in omega squared plus the optical frequencies squared. That's a way of rewriting the phonon action in Fourier variables both in space and time. And we would recognize this then as our little chi function, now written in frequency. If I pull this factor of h bar out, I have 1 over h bar omega squared plus omega LO squared. The Fourier transform inverse of chi of omega would give us a chi of tau. That then is the correlation function that would enter in after I do that the Gaussian integrals associated with the phonon variables. So integrating over that set of phonon variables, we would get the quantum partition function. We still have an integral over the electronic paths. We would get a factor of the phonon partition function. And in addition, we would have to our existing electron action an exponential. And we know what to expect. We get the linear coupling. So this piece and those all squared under extra integrals with this correlation function. That's what our normal Gaussian theory tells us we get. And indeed, so we'd square those prefactors, giving us now, instead of square root of alpha, alpha. We would get factors from this initial kernel. Now, instead of to the quarter root, to the square root, we still have sums over k's. There's no cross terms in k's because they're all independent. We get integrals now over two imaginary time points. Call it tau and tau prime. And underneath that kernel, 4 pi, the k becomes squared. We have our chi function at tau less tau prime. And now I, k dot, x of tau prime. Working out what chi of tau is, it's a factor of h bar in a Fourier transform. It's an integral one can do. Note that using a continuous Fourier transform, as I'm doing, is essentially assuming a low temperature limit where all frequencies are possible. So I have an infinite domain over this integral. That has a pretty simple form, just dependent on the optical frequency and decaying in imaginary time. So I have exponential correlations due to that, exponential correlations in imaginary time for the phonon variables. So if I combine the original action of the electron with all of this, let's call that S tilde. It is now the effective action we have gotten from integrating out the phonon variables through their Gaussian integrals, something we could do exactly. And we would get 1 over h bar, the original kinetic energy of the electron, now less alpha frequency squared, these factors coming from the strength of the interaction, two imaginary time integrals. I can write much more cleanly. Sum over k, 4 pi k squared, e to the I k x of tau less x of tau prime. Whoop. Sorry. Let's give myself a little more space. And now this decaying exponential. Like so. All right, that looks pretty ugly still. Sorry, one of those factors of the optical frequency should have canceled out with introducing chi over here. There's one last trick to make this a little cleaner. If we note the sum over k, 4 pi over k squared, that is a Fourier transform. The Fourier transform of 1 over k squared with a 4 pi is, so the Fourier transform 4 pi over k is equal to the Coulomb potential. So I can rewrite finally this effective action with all of that, but rather than having the sum over the wave vectors, I can use that Fourier transform to then write it as that correlator from the chi's and now, taking a step back, we find that integrating out the phonons gave us kappa kinetic energy. But in addition, we have now a screened Coulomb interaction acting on the electron at different imaginary time points. So if we thought about what we've just seen, we have our initial lattice with our path integral, our representation of the electron that moves around this imaginary time path, integrating out the phonons, we find we have an imaginary time path still, but now different points in that path interact with an attractive, it's got a minus there, alphas and omegas are strictly positive, everything else is strictly positive. So there's an attractive interaction between the points in imaginary time. That strength goes like alpha. For large alpha, this imaginary time path would get localized to a point. So this is a somewhat abstract way to understand the influence of the phonons on the electron, how it can act to localize it. Essentially, imaginary time, that's like saying that there is a delay in the action. So an electron interacts with a phonon, the phonons propagate through the material and can come back and act back on the electron. And the effect of that back action is to act to localize it. I think there's an intuitive understanding in terms of electrostatics. The electron polarizes the lattice. That polarization generates its own field, which is favorably back acting on the electron. And to the extent that that action is large, that interaction is large, the electron will essentially localize in space. The delay, or the screening, results, the characteristic time of that screening is set by the optical frequency, and the limit to that optical frequency is 0, it's unscreened. So there's it's a much stronger attraction acting on the electron, but in the limit that the optical frequency is larger, there is more screening, there's more scrambling of that polarization, and thus the effect of localization is weakened. Now, note, while the electron variable, I don't know why I started putting e's here. While the electron kinetic energy is quadratic in the electron variable, that Coulomb coupling means that we can't actually integrate out the electronic motion. We can't actually solve for the partition function. That nonlinearity makes that difficult. However, this treatment due to Feynman of the polaron problem can be approximated very well using a variational expression of the partition function. If I was going to take that quantum classical isomorphism, the partition function we've just arrived at, we have some phonon partition function. We have an integral over the electron path still weighted by this effect of electron action. That's the exact calculation of the partition function we would like to do, but the nonlinearity in the effective action makes it difficult. However, I can multiply and divide by 1, introducing some partition function, call it z0, which is an integral over an action s0. In addition, I can add and subtract s0 in the argument of that exponential, rewriting this as minus s0 plus s0 minus the effective action. I realize that the denominator of a partition function and the new weight associated with an s0 lets me write down the exact partition function now as a factor of the phonon partition function, the partition function of this reference, and an expectation value of s0 minus the effective action in this reference system. Now that doesn't really help me any. However, using the convexity of the exponential, I can bound this by taking that expectation value upstairs. Now this is useful if I imagine introducing an s0, a reference action, which was quadratic and thus computable. I now have a way of estimating my partition function by just doing a simple averaging over that effective action in a Gaussian system. So by introducing a quadratic reference action, we can at least bound the partition function. And further, if S0 is tunable, say it has a set of parameters say variational parameters, we could solve for an optimal set of those parameters to find the best bound that we could arrive at. And indeed, this was Feynman's trick. He introduced a quadratic action with a set of parameters that could then be optimize and yield essentially what is the most accurate treatment of this polaron problem. Actually going through that variational bound is kind of difficult. One actually computes with it things like the free energy of the excess electron given by that ratio of partition functions, which if the partition function is bound, provides an upper bound on the free energy. What I will leave for you all in the notes, since we're running a little late, is to go through, one could go through and take a reference action close to the non-interacting electron limit. So if I imagine averaging the path integral over just the evolution of the free electron, so where it just has kinetic energy, one could actually solve for the zero temperature limit of the free energy and show that it is bound by doing a couple more Gaussian integrals on that action. So now we have a harmonic system, that it is bound by alpha h bar, the optical frequency. So just to give you one extra step. So essentially we would need to compute the expectation value of the effective action in that low temperature limit. And one can arrive at an upper bound for the binding energy, which is minus alpha times h bar omega, optical frequency. The interpretation here being that in the small alpha limit, the weak electron phonon coupling limit, remember alpha is a dimensionless parameter that tells you the strength of the coupling. In that limit, the binding energy is just given by the number of excited phonons that the electron generates. H bar omega being the excitation energy for a phonon mode, all the phonons being the same, alpha being a dimensionless parameter, then tells you how many modes essentially are created as they solvate this electron forming a polaron. This actually limiting binding energy actually works pretty well even up to alpha being near a unit. So it is essentially quantitatively correct for gallium arsenide, where alpha is less than 0.1. And using Feynman's trick of actually introducing variational parameters and optimizing the action, in addition to the free particle contribution, he added a harmonic potential with an effective spring constant that one could tune. One can actually get variationally close estimates of the binding energy and the effective mass across a whole range of coupling constants alpha. Okay, so those of you who are interested in this question or in this problem can go through this last calculation through the notes, so I'm happy to talk about it in the small groups. And with that being said, we're essentially done with linear response or static response. And over the next few weeks, we'll be turning our attention to dynamical problems, time-dependent response, where essentially the same sort of structure will be made use of again, thinking about correlation functions now in time instead of space. All right, thank you all for your attention. Sorry I went a little over, and I look forward to talking to you all in the small group.